Hello, everybody. So we are going to discuss now one interesting method for the measurement of the volumetric flow rate, which is using pitot tube. So we discussed pitot tube before in chapter 5 when we were discussing the applications of Bernoulli equation, and um, quickly we can go through the details of the pitot tube calculation. So the main point of having a pitot tube is that the flow will go through this narrow tube, and is going to fill or push the flow, the manometer flow downward. And from this, at this point, or it will keep pushing until it reaches a point where it has no more energy to push anymore. So the velocity here is going to be zero because the fluid is stagnant, and because of this the pressure will be very high, and this is why we have the differential height in this manometer. And from the delta height, or the change in, or the difference in the differential height of the manometer, we can find the the velocity of the flow. But this is used to calculate or measure the local velocity, which is very important. Okay, so this is only for the velocity at this radius. Okay, so from Bernoulli equation, these points 1 and 2, which is this point and this point, are at the same height, and the velocity at point 1 is 0 because it's a stagnant point. And now we can cancel these three g's together, and then from this we can say p v2 is 2 times delta p over rho fluid. And if we know the density of the fluid and the density of the manometer, we can substitute with them to find delta p, like the example we solved last time. So simply this equation can be used to calculate the velocity with the knowledge of delta p, or the densities of the fluids and the height of the manometer fluid. And it's important to know what we mean by the local velocity. We mean the local velocity because the velocity varies with the radius, and that's something that we know from before, and we discussed it a lot this chapter. So you can move the pitot tube up and down inside the tube, so it can measure the velocity at this radius or at higher or lower radiuses. So it's not measuring the volumetric flow rate like the other devices. It's measuring the local velocity. So you can use it to get the velocity profile, which is very useful piece of information. We can collect the velocities at many or different radii, and from this we can calculate the volumetric flow rate, which is not the main goal of using the pitot tube, but it's a useful thing that we can get, like an additional information that we can get given the outputs we get from the pitot tube. And this is simply based on this information and this equation. I think we discussed it many times before, that you can calculate the volumetric flow rate as the velocity times area, or by integrating v dA over the whole area. Okay, and the velocity, which is function of r, and the area is dA is 2 pi r dr. And this is 2 pi, I got it out of the integration, and then r dr, and then this is the what we have inside the integration. Usually the information that we have for a case like this are all tabulated data. Like, at this radius, this is the velocity, this is radius, this is the velocity. So we don't have the velocity as a function. We have the velocity as numbers. So for this case, there is one thing we can do is to get this integration, which is the graphical integration. And this is very simple. What we see here is equivalent to this. If you draw a relation between RVR, which is this on y-axis, and R on x-axis, then the area under this curve is going to be the integration, or the value of the integration from 0 to R. Okay, so this is what we do in this case of pitot tube, that we can calculate the volumetric flow rate by graphical integration. And this graphical integration can be done with many methods. There is like the trapezoidal method, like Simpson method, and there are other methods that you can use to do this. So this is just to clarify how we can use pitot tube using to use pitot tube to calculate the volumetric flow rate. And this example is it shows some numbers that we can use to do this. So we have a 10 centimeter diameter pipe, and we can use it to calculate the or measure the or use pitot tube, I'm sorry, to measure the velocities at different radii from 0 to 5 centimeter. Of course, this is the radius, so it's from 0 to 5. And 5 is the walls of the pipe, so the velocity is 0, and u is the maximum at the center. And from this, we want to calculate the volumetric flow rate. I have already solved this example before using Microsoft Excel. And actually, at this point, I was trying to clarify or show how to use the trapezoidal rule or the Simpson's rule to calculate the area under the curve. So I'll put the link to these videos, the video, I think there are going to be two videos, one for trapezoidal and one for Simpsons. So I'm going to show the videos or put the links in the description, so you can discuss it or see it yourself if you're interested. Yeah. So I'll stop here, and I'll continue next time, inshallah. See you then.